I'm happy once more to talk to DefCamp. I am talking at DefCamp since 2018, and I am very happy that this year it's the first time in Cluj. I enjoy Cluj very much. It's a very beautiful and wonderful city. By the way, I'm already almost local in Romania, because this year I was in Bucharest. After that, I was in Brasov, checked your palace, checked your castle of Dracula, so enjoyed everything. Wonderful country. So, a bit about me. I'm working, of course, in cybersecurity. My major direction is cryptography. Of course, I love ethical hacking. Sometimes I'm involved in different penetration tests. Sometimes I lead penetration testing teams and so on. But my major focus is cryptography. In Georgia, I work at university, Caucasus University. We have a cybersecurity center at this university. At this university, I am professor, and I am the director of the cybersecurity center. I want to emphasize that in the university, we are using CyberEdu platform, which is offered by DefCamp. It's your national platform. We are using it for teaching, and I will say it's very good. We enjoy a lot. Also, I represent Scientific Cybersecurity Association, which is the largest cybersecurity entity in Georgia, NGO, and I am the president of this association. So, all of us know that the world, the scientists are working on creating quantum computers. We will work, of course, more about it in details, and it's a wonderful weapon in today's war. The country who will create a quantum computer, I can say that it will be the leading one in the real war, because quantum computers, as you will see very soon, can break today's crypto systems, today's asymmetric crypto systems. And there is an organization, NIST, N-I-S-T, which tells us that, okay, guys, this crypto system is a standard, and you can use it. And there is one standard obtained, concretely post-quantum standard. What post-quantum means? Post-quantum means that it can be usable in post-quantum epoch, and it resists the attacks of quantum computer. This system is called Kyber, and there was a paper that some of the researchers broke it. And there is, guys, very big debates. Is the system broken or not? Can we use it or not? So, therefore, me, under my leadership, my team, decided to analyze this attack, and today I will offer you the detailed analysis of this attack, and we will decide together, of course with my recommendations, is the system broken or not? During this attack, I want to say that, of course, artificial intelligence was used, because today, as you have mentioned, as you have paid attention during all these 2 days, all of speakers are talking about artificial intelligence, because it's a very relevant topic today, and it's widely used in cybersecurity. So, is post-quantum standard Kyber broken or not? Thanks to our sponsors. I am very glad that they are supporting DefCamp, and we are today here. And let us make the small overview of cryptography, very small overview. Here we have 2 actors, Alice and Bob. Do you like how I painted them? It's not me, it's artificial intelligence. And here is Mr. Hacker that is trying to intercept the cipher. So guys, what is going on? Alice is going to send Bob the message, but she doesn't want somebody to intercept this message and to read it. So what she does, she encrypts the message using, she has special encryption algorithm. She has some key which she has shared with Bob. How they shared, it's already another issue. And she encrypts the message with the key, gets the cipher, and afterwards she sends the cipher to Bob. Here is our handsome Bob. He takes the cipher, only he has the key, only him has the key, and he decrypts the cipher and gets the message back. Here is our wonderful hacker who is trying to read the message. He intercepted it, but he doesn't understand what is written there. Why? Because he doesn't have the key. So guys, what is important? Then that after decrypting the encrypted message with the same key to get the message back. This is, guys, the basics of symmetric cryptography, so-called private key cryptography. Why it's called symmetric? Because we have only one key. On one hand, we encrypt with it. On another hand, we decrypt with the same key. Let us continue. So, for symmetric cryptography, we use AES standard, which was standardized by NIST in 2000 here. And as I told you, NIST is an organization which is used for standardization of crypto algorithms. And if NIST says that it's standard, we are using it. This AES was taking part in the competition, which was lasting for 3 years. And in 3 years, NIST said, OK, guys, use it. So it's a wonderful algorithm, and there is no any clue to use anything else for symmetric encryption. This algorithm has the block length 128 bits, and the key length is 128, 192, or 256. For today, 128 is enough, but if there is quantum computer, we will have to double it and to use 256. So for symmetric cryptography, quantum computer doesn't do anything dangerous. We just double the key. So there is no any problem. But the problem is for asymmetric, for public key cryptography. First of all, let's quickly look how it works. Here I have another heroes, the same Alice and Bob. So Alice generates public key and secret key. She uploads her public key to some repository. She will upload and write Alice public key. So everybody, guys, who wants to encrypt the message will go to repository and use Alice public key and encrypt the message. As you understand, the encryption is being done by the public key. So we take our encryption algorithm, our message, our public key, and get the cipher. Afterwards, Bob sends the cipher to Alice, and only Alice can decrypt the ciphertext because only she has the secret key. So everybody, guys, can encrypt the message, but to decrypt the message can only that person who has the secret key. One of the most used asymmetric crypto systems today is RSA. And look how it's used. I will very shortly explain to you. I won't go very deeply to formulas. I will try to keep it as simple as possible. So she generates 3 numbers, N, E, and D. For the public key, she uses N and D. And for the secret key, she uses D. To get the message, she takes cipher to the power of D in mod N. Afterwards, to decrypt, Alice takes M in the power of E and gets... sorry, guys. So to encrypt the message, Alice takes it in the power of E, gets the cipher, afterwards sends the cipher to Bob, and to decrypt the message, Bob takes the cipher into power of D, and he gets his message back. This crypto system is based on the assumption that cryptography is not the very strict science. It's based on mathematics, and concretely, this crypto system is based on mathematical assumption that it's very complicated to factor the number into two prime numbers. I will tell this as simple as possible. For example, we can multiply two simple numbers by each other, but afterwards it's very complicated to factor them when the numbers are sufficiently big and in the concrete conditions. So RSA is based on complexity of factorization problem. All good, guys. We can use RSA. There is also elliptic cryptography. We can use elliptic cryptography, and the life is good. But as we talked, quantum computers are being created. So, bless you. In 2013, as I remember, we read the paper that Google signed the contract together with D-Wave, and D-Wave is very global, the very global organization who produces quantum processors, and they signed the contract to work together. So at the time, our team began to work in this direction, and as I told you, quantum computer is able to destroy all asymmetric crypto systems, for example, RSA. And RSA is used everywhere in a lot of products. Can you imagine, guys, your SSL protocol, HTTPS, you are going to website. It uses asymmetric cryptography. All your communication will be cracked. So all this is going forward, and in 2019, October 23, Google has announced that they have reached something called quantum supremacy. What is quantum supremacy? So today, we are using Newton physics in our computations. And it's classical physics. And quantum computers will use quantum physics. And quantum supremacy means that quantum physics is used. And Google has claimed that their computer, Sycamore, has really reached something like quantum supremacy. You know that IBM is working to create supercomputers, and Google compared Sycamore to IBM's computer, which was called Summit. And they said that they took the task, and they completed this task in 200 seconds, but IBM Summit computer would need 2 days and a half to accomplish this task. Of course, IBM didn't like this news. Immediately, they wrote the response that they don't need 2 days and a half. They need only 2 hours and a half, but still 200 seconds and 2 hours and a half. So there is already something like quantum supremacy. All good, but here are our Chinese friends. In 2021, the Chinese research team have announced that they have got the wonderful progress in superconducting, quantum computing, and in photonics quantum computing. So they created the quantum computer using the property of the light, of the photons. And their computer, guys, is 10 million faster than IBM supercomputer, and 1 million faster, 1 million times faster than Google's quantum computer. They called their computer Zhu Hong Xi, I think I spell it correctly, 2.1. And after this, of course, NIST began to think about accepting post-quantum standards. because Chinese went really ahead. Of course, all this is according to official information. None of us knows what is going on in reality, yes? This is what can I tell you according to the official information. And of course, the scientists, the researchers like us, are working on creating post-quantum crypto systems, and there are four directions for creating. The first one is hash-based digital signature schemes. Their security is based on the security of the hash functions which they use. It's the most, if you ask me, easy one, but you can create only digital signatures with it. We have a NIST standard on it. I will show you afterwards, very soon. Another one is code-based public key encryption system, which is based on code encoding, and one of the very famous system, code-based, is McEllis crypto system. Another one is lattice-based cryptography, about which we will talk today a lot. This one was, as the scientists claim, broken. We will talk about it. And lattice-based cryptography, it's based on worst-case hardness. It's based on lattices. I don't know if you know what is lattices in mathematics, but they are vectors. And as I told you, cryptography always is based on some mathematical assumptions. And lattice-based is based on the assumption that it's very complicated, it's very complex to find the closest vector. It's so-called the closest vector problem, CVP, and it's very complicated to find shortest vector. So SVP, shortest vector problem. And the last one, I didn't deal with it at all. The only papers about it I saw from Bernstein. It's a very complicated one. It's multivariate public crypto system, where we have a set of quadratic polynomials over a finite field, and we are working on it. We don't have any special results in this direction, where I mean in the world, I think because it's very complicated for now. It uses very complicated mathematics. So guys, here is our NIST. And finally, NIST has announced that it has selected crystal Kyber algorithm for encrypting the messages. And concretely, this one was announced to be broken. In the next slide, you will see it. So they used crystal Kyber for encryption, and it's lattice-based encryption algorithm. And for digital signatures, NIST has selected 3 algorithms. Crystals, dilithium, Falcon. These two use the same mechanisms that crystal Kyber. Both of them are also lattice-based, and Sphinx Plus. Sphinx Plus is hash-based. It's less efficient, but it's different. If lattice-based are broken, we can use hash-based. Here is our paper, which called the big house. In 2022, July, the scientists from Stockholm, Sweden, which worked in Royal Institute of Technology, have announced we have broken crystal Kyber. Crystal Kyber we have broken, they said, and we used artificial intelligence for it. We know that we are in the epoch of artificial intelligence, and everybody is using it, me, you, all the scientists, and they have announced that they have broken it. Let us analyze this attack. First of all, what is Kyber? How it works? So Kyber is CCA secure. What is CCA secure? That you cannot break it, and you cannot mutate the messages. What does it mean? If I am sending to somebody $100, the attacker mustn't be able to change it on $5,000. So this means CCA security. And Kyber is CCA secure key encapsulation mechanism whose security is based on LWE, so learning with errors problems. It is lattice based, and learning with errors is the same complex as SVP and CVP, closest vector problem and shortest vector problem. So Kyber is one of the finalists. Is in the list of the standards by NIST. So there exist different options of Crystal Kyber. The attack, which we will analyze today, was performed on Crystal Kyber 512. We can compare Crystal 512 is the same that IS 128 with the key 128. Kyber 768 is the same as AES 192, and Kyber 1024 is the same that AES 256. And the scientists who have created it tell us that if we use Kyber 768, it's absolutely enough, and it's absolutely secure in post-quantum epoch. So, guys, here is a small scheme. Diffie-Hellman, what is Diffie-Hellman? It's an algorithm of key management. So we can exchange the keys using Diffie-Hellman algorithm. And they use very similarly, they work. The only thing is that by Kyber, here we encapsulate the public key to get a shared key and ciphertext. It's the only difference. So here is an example of CPA secure implementation of Kyber. Not implementation, but algorithm. What is CPA? CPA secure, guys, is when it's secure against cracking, but it's not secure against malleability. So hacker can change the cipher. And I will tell you very briefly how it works. For key generation, we use, as you can see, some matrices. Finally, we apply some formulas on them, and finally we get public key and secret key. For encryption, we also use some mathematical formulas on these matrices and get two vectors, U and V, and this is our cipher. And also here are some formulas applied on the vector to decrypt it. And then what is interesting, because the final results were CCA secure, here is approximately the same methodology, but everything is hashed. Public key we hash, cipher we hash, and so on. Why do we need hashing? Because when we take the hybrid of symmetric and asymmetric cryptography, we get CCA security. So if we make all this correctly. So this one is already CCA secure. And the scientists, when they attacked Crystal Kyber, they not only used artificial intelligence, but they used side channel attacks. Side channel attacks are very dangerous and important. What are side channel attacks? Sometimes our schemes are absolutely mathematically secure, but they are still side channel, they are still vulnerable against side channel attacks. So what is side channel attack? When the hacker measures time, looks, we needed 5 seconds, 5 milliseconds to encrypt the message, to decrypt the message. In this time, we needed 5.50001, and he gathers as more data as possible, and by means of this data, afterwards he makes the attack. Also, the attacker can measure the power, and measuring the power, he can make the same type of attack. It's, by the way, very dangerous, particularly for embedded system, because they use, for example, electromagnetic radiation. And of course, hacker can measure it, gather a lot of data sets, and in today's conditions, use machine learning to conduct the wonderful attack. So, NIST tells us that despite of the fact that I accept the standard, continue checking it on side channel attacks. Because side channel attacks are very often and very dangerous. So, researchers, of course, began to study side channel attacks on the new standards. They are happy to break something. And we use researchers to make beautiful words. Maybe we can say hackers began to study this type of attacks. And they were interested, of course, to attack CCA secure implementation of Kyber, and they used Fujisaki Okamoto transform, message encoding decoding, number theoretic transform, and error correcting codes in order to gain as more information as possible. All these operations which I mentioned are used for encrypting the message. And they have focused only on one algorithm. They have focused on decryption algorithm, and they used vertical side channel attack. What is vertical side channel attack? There exist two types of side channel attacks, horizontal and vertical. Horizontal are more common. Horizontal, when you are checking everything, when you are trying here, everywhere, in every function. And vertical side channel attack, when you choose one function, focus on it, and are exploiting it. So they used vertical side channel attack. I will show you afterwards the function on which they focused, and they used the hardware, so-called M4 scheme. I will show you this hardware, and they succeeded to retrieve, to get the keys, absolutely the whole keys, using this attack. Also, they used flipping and message rotation for it. What is flipping and message rotation? I will also show to you. Because, guys, when you read this paper, you will not understand anything. There are a lot of new terminology when even a lot of high-level cryptographers don't know. So you have to make the analysis of it to understand what's going on. So, in order to protect against side channel attacks, masking is being used. So I will also explain to you what is masking. And the researchers concretely attacked already masked implementation. They chose mask implementation, and by means of attacking it, they have explained that you need more serious countermeasures. About these countermeasures, I will also provide my recommendation. So what is masking? For example, if we have the secret, the cipher X, we divide it into, for example, if it's fourth level mask, we divide it into 5 pieces. If it's 5-level mask, we divide it into 6 pieces. If it's X-level mask, we divide it into X+1 pieces. So they divided. They used W orders. For W order masking, we divide the secret into W+1 pieces. And all these pieces are used independently. They don't leak information about secret. And afterwards, to collect together the secret back, this formula is used, and this circle, I will talk about it. This circle can mean different operations. I will talk which operation it can mean. So, this circle can be or arithmetic addition, or it can be Boolean. If it's arithmetic addition, we just use plus. If it's Boolean, we use XOR. We use XOR operation instead of this circle. And so when it's masked, the computations avoid involving X directly. So you don't see the secret, you see only the pieces of it. And when seeing the pieces, there is no chance. No, there is a chance, but it's complicated to get information about the secret, about X. So, as I told you, the hackers, the researchers, used AI in order to improve the attack. And they used something called recursive learning. It's the direction of deep learning. They claim that it's the direction created by them, but it's not like this. I've met it in other papers also, so it was not something know-how. The cyclic rotation, I liked the idea. But about recursive learning, it was nothing new in it, I will tell you. And so by means of this recursive learning, they have really increased the speed of the attack, the speed and efficiency. They made it much, much more efficient. And by means of it, they absolutely retrieved the shared key. So they found that the decapsulation procedure, as I told you, is a vertical side-channel attack. They focused on the decapsulation procedure and broke it. When they have got the shared key, they double-check that the shared key was not changed, and afterwards they began to work on it, and they gathered a lot of patterns, and afterwards, based on recursive learning, they broke into. So here is a small diagram. This is a data set for the fourth order mask. This is the data set for the fifth order mask. Here is already trained weights of batch normalization for the fourth mask and for the fifth mask. Look what they do. They repeat it and afterwards add the new piece. Because of it, it's called recursive, like recursion. They use the previous and only afterwards add the new piece, and afterwards they train it and they got something like this. So what was, as I tell you, really interesting for me, another contribution, so-called cyclic rotation. What is it? They have found that the first bit of the cipher leaks much more information about the message than the next one. So they have understood if they compare the first and the eighth bit of the message, the difference of the leakage is 9%. So 8th bit leaks 8% more than the first bit. It's a big problem. And they created something like rotation. I will show you what they did. This one was really innovative and beautiful, what they did. And they attacked concretely this function, which was called masked poly from message. This procedure was not uniform. They found that it was not uniform, and they attacked it using cyclic rotation. Here is a small code. If you know a bit of programming, if you know 4 cycles, look what they do. They take the cycle from 0 to 8, and they rotate the bits. They rotate the bits. They put the first one, the 8th one, the second one, the 9th one, and like this, they rotate it in order to decrypt the message easily. So, guys, here is that board on which they made the experiments. It's called Chip Whisperer board. It has Cortex M4 CPU and downclock to 24 megahertz. Power usage is sampled at 24 megahertz, where the precision is 10 bit. So they have gathered 150,000 of power traces. They collected it by means of decapsulation of different ciphertext for the same key-EM pairs, key encapsulation mechanism pairs. It's already very strange. It's already very strange, because key-EM pairs must be always different. And they made it for the same key pairs. This is already strange. This is not like this in real life, because they change. I must emphasize that we can use long-term key-EM pairs for hybrid public key encryption and for encrypted client hello protocol. But still, in some period, this pair must be changed. And the scientists didn't change it.